All right, AP Physics, here are your most missed questions for the work and energy section for multiple choice. Here's your first one. A nonlinear spring is used to launch a toy car. The car is pushed against a spring, compressing it 2.5 centimeters. Force the spring exerts on the car is given by the equation. Here it is. And they give us the K value. They want to know the potential energy stored in the spring. So a lot of spring ones in this. And we have a couple of the most missed ones being spring ones. They all have this same relationship here. You might have been tempted to try to evaluate this by saying your force is equal to negative K times X, which is Hooke's law for a spring, a linear relationship between your force and your displacement. If this is true, the general equation for the potential energy stored in the spring is 1/2 kx squared. Well, this potential energy comes from the integral of that force. It's the negative integral of that force from 0 to x for your displacement. So we can only use this, the potential energy function here, if our force is linear. And it's not in this case. So we can't use it. Our force is not linear. It's a squared relationship. So we have to go back to calculus here. And we're going to calculate our potential energy by taking the negative integral of the force over the displacement. And if you plug that in for our initial position and our stretch position and evaluate it, you get 0.026 joules. So the negative here is required because the force that the system exerts is going to be the work done on the block or whatever is attached to the spring. And we want to know the potential energy stored in the spring, not the work done by the spring. And that's what the negative is. They're inverses of each other. In other words, if you take a spring and you stretch it, you're storing energy in that spring, which we want to have a positive value, which we do have here. And that stored energy is going to be positive only because we add the negative sign here. Okay. Our next one is also a spring. A specially designed spring is stretched from equilibrium to the distances x given in the table. And we get the restoring forces recorded as well. What's the potential energy of the spring when it's stretched 3 meters from equilibrium? You might have been tempted to just go to 3 and look for 27 and say, well, there's my potential energy. This is my force. It's not your potential energy. And from that force, we really can't directly get our potential energy. We need to look at how force depends on your position. And you want to see, again, does it obey Hooke's law? If it does, then we'd have a linear relationship here. In other words, this would go up with consistent values between these as you increase. If 1 to 2 would have the same jump as 2 to 3. We don't see that here. We get increasing differences on this side, so we've got a little bit of a curve here. And the best way to see that's not Hooke's law is to graph it. And if you graph it, if it was Hooke's law, you'd end up with a nice straight line here. And we don't end up with that. We end up with this curve. And we want to know what's the equation for this curve. Force as a function of x so that we can integrate it to get our potential energy. Well, you could probably figure that out by looking at your numbers here. You could plug it into a calculator. But 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So our force is related to our displacement by a cube relationship. And then we need to put a negative in here. Again, if you stretch a spring, as I stretch it to the right, it's going to have a force that goes to the left. If I stretch it to the left, it'll have a force that goes to the right. And that's what the negative is here. So once we have our force function, we can integrate it over our bounds. We're going to start equilibrium and stretch it to 3 meters. And if you do the integral, our negatives turn to positive and we get 81 force joules. We want a positive value because we stretch the spring and we're storing energy in it. And that's one of your multiple choice options, 81 force. Okay, our next one. Suppose potential energy of a particle constrained to move along the x-axis can be described by the function, and it gives it to us there, where k and a are positive constants, stable equilibrium points about which the particle oscillates are located at. Quick refresher here. How do we get stable equilibrium for a potential energy function, for any function that looks like, well, any curve? The bottom of these little curves are the stable equilibrium points. In other words, you can picture that like taking a ball here and letting the ball roll down the slope. It's going to roll down this slope and back up on this side, and it's going to oscillate back and forth around the stable equilibrium point. Another way to think about that, if you put the ball right at the bottom and you let go of it, it's just going to stay there. And it's stable because if I give it a little nudge, it's going to keep oscillating back and forth around this. These ones are unstable equilibrium points. And unstable ones, you could have the ball at rest at the top of the curve. If you give it a little nudge, it's going to take off, and it's not going to return back to this curve. It's just going to continue going. That's an unstable equilibrium point. So we want these minimums at the bottom for this particular graph. How do we get a minimum? Quick refresher for your calculus. You want to take the first derivative of this, and the minimums here are going to be points where the slope of the line is 0. So I want my first derivative to be equal to 0, and it's a minimum when your second derivative is positive, so you get concave up for your equation. So my first derivative for this would be 2 times 1/2 is just 1, so I get k x minus alpha, and my second derivative with respect to x is just going to be k. So it's positive for all values, k is a positive constant. It's a concave up, an upward opening parabola, and that allows us to say that the only value that this is 0 at is going to be a minimum. So let's set this equal to 0. We get k times x minus alpha. Add alpha to the other side and divide by k, and you get x equals alpha over k. And so it actually looks like this for a function. We get a parabola, upward facing parabola, and this point right here is going to be alpha over k. And that's your answer, and that's one of your multiple choice values. Another thing that you want to be aware of for potential energy functions is the slope of your potential energy function is the negative derivative of your potential energy. It's a negative force. So if you take du dx, this is equal to negative force value for it, which will show up here in a second. A block of mass m is attached to a spring and placed on an inclined plane. The spring has a spring constant k, and there's negligible friction between the block and the inclined plane. The block is released from rest at the position shown in the figure, and the spring is initially unstretched, so we're at equilibrium when we release it. What distance d does the block slide down the plane before coming momentarily to rest? If you thought about this problem and thought the momentarily to rest, and you tried to solve it like this, you're probably not alone, where you said this distance d, the block's going to get down this distance d, and it's going to come to rest when the force of the spring is equal to the force of gravity acting down the plane. You're probably not alone in thinking about it that way, but that's incorrect, because what actually happens here is the block starts to accelerate. In other words, at first, if I draw some forces on here, at first there's no force of the spring, and there's only the force of gravity going down the plane, the component of that. I'll call Fg in the x direction as x goes down the plane. Well, as it goes down the plane, this doesn't change. The force doesn't change here. But there's some point in the middle here where as it's accelerating, so we're getting faster and faster and faster, we reach this point in the middle where we have some velocity going this direction, and the force going down the plane here, Fg in the x direction, is now equal to the force going up the plane, F of our spring. Well, this is not going to have the block stopped. All this is going to do is make it so the block has no acceleration at this one point in time, but it still has a velocity because it gained speed as it went down to this point. This would be our new equilibrium point for the block. And if we were doing oscillatory motion, it would oscillate around this point right here. So we need to continue to go beyond that and figure out where does it lose all of its energy. That's how you want to think about this. As it goes down, once we go past this point, the force of gravity is now going to be smaller than the force of the spring. So as we get down somewhere in the middle here, the force of the spring is greater, and it's going to be decelerating, and it's going to continue to decelerate to reach the bottom here where velocity equals 0 meters per second. So how do we calculate that? I don't know if I have a second slide here. Nope, I don't. So let me clear my ink off here, and we will do a quick calculation for that. So I want to use an energy approach for this. At the bottom, my velocity equals 0 meters per second. So I start out with no kinetic energy. I end with no kinetic energy. What's changing for energy then? Well, I release this, and it's moving this distance here. This would be my h for mgh. So I have a potential energy gravitationally getting converted into the potential energy of the spring. And it's 100% conversion because we're going to have no kinetic energy at the end. In other words, all gravitational potential energy turns into spring potential energy. So this would be mgh equals 1/2 kx squared. And x would be the distance that the spring stretches. In this case, we're starting at equilibrium, so it's going to stretch the same distance that the block moves. So d is going to be the distance that our spring stretches. So this would be 1/2, and it asks us what distance d does the block stretch. So I'm just going to call this, we'll call it d, like our problem says. So d squared. H, how does h relate to d? Well, it's going to make this little triangle here, and we make a right angle, and this would be theta, and I want to know this displacement on the right side. That'd be sine. So I get mg sine of theta times d, the hypotenuse of my triangle, and I want to solve this for d. Well, one d cancels, one of the d's does, and then I solve for d, multiply by 2 and divide by k, so I get d equals 2 times mg sine theta over k. And that is one of your choices on your multiple choice question for that one. That's how you solve it. Okay. If it asked where the acceleration was 0, you would solve it for that force being equal for the spring as the force down the plane for gravity. All right, there's 2 problems that were similar to this one. I just chose one of them that were missed by quite a few of you. A student uses a heavy ball. This would be a great question for a lab-based problem on the AP test. A heavy ball attached to a rope in a pendulum experiment. The ball is hanging so the rope is vertical. The student pulls back the ball, releases it from rest as shown, and it goes back and forth. They compare the measured value to expected value for the speed of the ball at the lowest point. So once it gets down to here, it has some speed. They actually measure experimentally, and they find that the speed down here is slower than they expected. Which of the following may account for a slower than expected speed? The most common thing to jump to say air resistance, but for a pendulum, it's not moving fast enough for air resistance to play a large impact on it. Friction up here might play a larger impact than that, but the things, so C is not correct. You can't have air resistance. These low velocities wouldn't be a large enough impact for that. So the thing that they consider here, and the correct answer is B here, the student did not account for the mass of the rope. Why does the mass of the rope matter? Well, as it gets to the bottom of its arc here, when it's swinging, the rope is also moving. So each one of these points, you can think about it as tiny, tiny pendulums, little balls hanging on the end of a massless rope. Well, each one of these has its own velocity as well. So what does that mean? That means the potential energy of the system, where the center of mass would not be right in the dead center of the ball, release would be slightly up the rope, not very far, it'd probably still be within the ball. But that center of mass of the system, as it moved this distance h, all that energy gets converted into kinetic energy. But some of that kinetic energy is distributed to accelerate our rope, and some of it's distributed to accelerate the ball. So they forgot to include the mass of the rope when they released that. Our next one, an object pushed into a non-ideal spring again. Compressing the spring, the magnitude of the force is plotted up here. And the compression shown. Which of the following graphs best shows the potential energy of the object spring system as a function of x? So potential energy, you want to figure out how does force relate to the potential energy graph. And we wrote this a second ago, but the derivative of your potential energy graph is equal to the negative force value. It says here it's just the magnitudes of the force. So that means that we don't need to worry about this negative sign here. The magnitudes of the force would be just positive values. So the slope of your potential energy graph is going to be equal to the values on your force graph. So what's happening to our slope? Well, it starts out as a really small positive number, and it gets more and more positive as it goes up. So I should have a slope that's positive on my graph. If I'm looking for a potential energy graph, it starts out positive, a small positive, and then as it increases distance, so as my x value increases, my slope increases. So it should look something like this. It's going to be very similar to the graph that is shown right here for the force function. So where do I have that? Well, this one has the same slope the whole time. So this would be a constant force. The force function for this potential energy graph would look like this, just a straight line. So it's not that. The force function for this graph would be a negative one, and so it would look like this down here below our axes. And the correct answer is C here. My slope is positive. It starts out positive. It starts out at 0, sorry. And then it slowly gets more and more positive, and that's why C is the correct choice. This one would start out as a high positive value and decrease over time. And this one would start out as a negative large value and get closer to 0 over time. Okay? And that's it for this particular multiple choice set for questions that were most missed. I hope that helps. And if you have other questions that didn't get answered, please feel free to ask me.